So let's just get started. Um, okay. First off, we have PWM versus CAN. So for PWM, which is pulse width modulation, that allows production of variable analog signals using digital means. So the pros of pulse width modulation include simple connections and streamlined code, and the cons include that there are fewer options for motor controllers. Next, we have CAN, or Controller Area Network, which allows microcontrollers and devices to communicate with each other without like a host computer. So like it's basically a giant loop kind of connecting everything, which starts from the Robo-Rio and ends with the PDP, or power distribution panel. And the pros are that there's more functionality for advanced motor controllers, and it can send encoder data over the CAN line. But the cons is that the entire system can shut down if like any part of the loop breaks, and that it requires more complex wiring and programming. So I put a picture here of like Christmas lights because like do y'all know like how like old school Christmas lights work, or should I just like briefly explain it? Okay, I'll briefly explain it. So old school Christmas lights, how they work was that like they're all wired in series. So like each light was connected to each other. And so if one of the lights just broke, then everything broke because like since that light meant that like there's like the whole like circuit like open already. So like because of like the series wiring. So like if one light breaks, then like entire thing goes down with it because like you can't like there's a break in the connection because of how it's like a big loop. Okay. Mm. Okay, next we are going to explain wire gauges. So there are two systems, the American wire gauge, or AWG, and metric gauge. So we use AWG, and how it works is that it's basically like an inverse sizing system. So like a smaller value is going to equal a thicker wire, and a larger value is going to equal a thinner wire. So you can see from like the pictures like how like the size like varies, and how like 0 is like the thickest wire, while like 30 down there is like the thinnest wire. And like this picture also shows that. Meanwhile, metric gauge, which again we don't use, the gauge is calculated by multiplying the diameter times by 10, and it's very straightforward because it's just like the value of like the diameter times 10. Like so, like the smaller value would be a thinner wire, and the larger value would be a thicker wire. So here's some wiring requirements for like a lot of the like components that we use. Like we have the PDP Lego connectors and motor controllers, the batteries of which we use for AWG, which not every team uses, but like that's what we use, and like all that kind of stuff. And the reason why these sizes are the sizes that they are is because wires that carry a lot of current need to be larger, so they have less resistance, because more resistance means that like the amount of power kind of wastage, shall we say? Okay, that's not really a good word, but like more resistance would equal like higher heat dissipation, which would cause the wire to burn up. So that's why like the wires have to be larger so that the wires don't burn up. So now we have the power distribution panel. So this distributes power from like the battery to various components, and it uses CAN connectivity to communicate information about the robot's power. It connects to the Robo-Rio voltage regulator module, or the VRM, and the pneumatics control module, or the PCM. And it can report the current temperature, the bus voltage, the current draw for the total robot or from each device, and the total robot energy use. Okay, next we have the Robo-Rio, which is the brain, like the main robot controller. It includes like a variety of communication protocols like Ethernet, USB, CAN, and whatnot, along with like PWM, servo, digital, and like analog I channels to like connect to the robot peripherals for sensing and control. So it connects the VBAT controller PWR terminals on the PDP for power, and it can have wired communication via USB or Ethernet. It hooks up to the pneumatic control module like CAN, or like directly with the PDP CAN if PCM isn't used, motor controllers or PWM cables, and the robot signal light. Okay, next we have the voltage regulator module, or the VRM, which is the independent module powered by 12 volts. It's wired to like a dedicated connector on the PDP, and it connects to one of the two terminal pairs labeled the VBAT, VRM, PCM, PWR. It has multiple regulated like 12-volt and 5-volt outputs, as you can kind of see here, and it provides regulated power for the robot radio, custom circuits, and the IP vision cameras. So the two connector pairs associated with each label have a combined rating of what the label indicates. So like five volts for like 500 milliamps total for both pairs, if not for each pair. And the 12 volts at 2 amps limit is the peak rating. So the supply should not be loaded with more than 1.5 amps continuous current draw. Okay, next we have the PCM, which we do not use, but still important to go over. And contains all the inputs and outputs needed for 12 volt or 24 volt pneumatic solenoids and the onboard compressor. It's enabled or disabled by the RoboRio over the CAN interface. It has an input for the pressure sensor. When there's a solenoid that is coded for and controlled, the PCM can control the compressor automatically when the robot is enabled, and it collects diagnostic information such as solenoid states, pressure switch state, and compressor state. So like the solenoid states are like work with binary states, so it's either the max length or like protracted. The pressure switch is just like open or closed based on like whether like the pressure threshold is met, and the compressor is just compressing or maintaining like maximum pressure for the two main states. It also includes the diagnostic LEDs for both the CAN and the individual solenoid channels. Okay. Okay, next we have the radio, which is just a wireless radio, and like we use it for the wireless communication functionality for the robot, and like options that we can use equal like the mesh like that and that. So it's powered by the 12 volts at 2 amps output on the VRM, and it's connected to the RoboRio controller over Ethernet. So power over Ethernet, or PoE adapter, is used to power the radio, which you can see right here. It can be configured as like an access point for the connection for a laptop wirelessly, or also as a bridge for use on the system, which can connect to FMS or field management system. Okay, now let's move on to circuit breakers. So there are, I guess, two types of circuit breakers. The main breaker, which is 120 amps, it's the main like power switch, and it's a protection device for like downstream like robot wiring components, and it's wired to the positive terminals of the robot battery and power distribution boards. Next are the PDP breakers, so they can be 10 amps, 20 amps, 30 amps, or 40 amps. The 10 amps is the smaller 20 amps. The PDP breakers can be used for VRM, RoboRio, or PCM. 20 amps for the motors for manipulators that don't draw like much power. 30 amps for motors that draw like a medium amount, and 40 amps for motors that have a high load. So it's used with the PDP to limit current to branch circuits, and like the value of the amp, it determines the size of the PDP channel the breaker is used in. Sorry. Okay, next we have sensors. So okay, my cat is being annoying, but let's first go over limit switches. So like these are sensors that can tell you like just like if a component is touching or not. Like they're just like mechanical sensors, and they don't plug directly into the motor controller, but you can use a normal PWM cable to wire it to the RoboRio. Next is the NavX. So this is a 9-axis sensor. So it has like accelerometer, like gyroscopes and magnetometers like all together. It like allows tracking of a robot's like heading, and it connects to the RoboRio like MXP connector for both power and data. Next, we have the SRX mag encoder, which is a rotary sensor. It can be used to like measure rotational position and velocity, and it has both a quadrature I can't interface, which can be used for like relative position measurements, and PWM output for absolute position measurement. Okay, next we have the robo signal light, which is pretty just basic. Like it's mandatory and it's just a sign of the robot's status. So like the solid on would mean that the robot's on and disabled. Blinking would mean it's on but enabled, and off would mean that the robot's off, the robo wheel is not powered, or the robot signal light isn't wired properly. Yeah. So next we're going to start talking about some motor controllers. So first up we have Spark. So it controls motor speed for brush motors, and it's controlled using the PWM interface. Sensors have to connect to a motor wheel because they can't connect directly to a controller. And the like RGB status LED displays like the state of the device, like if it's in brake mode or coast mode. The brake mode is when it's applying power to stop the motor from moving, while coast mode is allowing the motor to keep spinning from like the inertia after power like is gone. Next, we have Spark Max. So it controls motor speed like with either traditional like brush motors or like brushless motors. It can be controlled over PWM, CAN, or USB for configuration or testing only. And it has a data port for direct sensor connection. It has capability for closed loop control modes when controlled over CAN or USB, and there's an AC control option, but not really used often. Okay. Next, we have the Talon SR. It controls motor speed and it's connected over the PWM interface. It's connected to a PWM output of the river wheel and powered from the PDP, and the LED indicates like the direction and percentage of throttle and state of calibration along with fault state. So a fault state, a fault can be like caused by like under voltage, over temperature, or shorted like output transistor, and having the LED like show that when there are like potential problems is useful for finding the source of the problems and preventing further damage. And also this motor controller is very similar to Spark. Next, we have the Talon SRX, which is a CAN-enabled smart motor controller. This can be controlled over the CAN bus or the PWM interface. And when using CAN bus control, you can take inputs from limit switches and potentiometers, encoders, or similar sensors to perform advanced control, like limiting and PID, closed loop control. Next, we have Victor SPX, which is a CAN or PWM controlled motor controller. It's connectorized to allow easy connection to the RoboReader PWM connectors or a CAN bus chain. It has a number of closed loop features also which is also present in the Talon SRX when controlled over the CAN bus. It has a sealed case to prevent debris from entering, and it's similar to this Talon SRX, but it's smaller and doesn't have an encoder port. Okay, next we have the Talon FX, and just say like this is a picture of the Falcon 500 motor with like an integrated like motor controller, because I couldn't really find a picture of like the Talon FX by itself, so I just included this. But this overall thing is a motor, not the motor controller. So Talon FX, it has CAN and PWM communication protocols, and it has a sensor integrated into like the controller, which is necessary for like brushless communication, which allows the user to use Talon FX with like a high resolution sensor without attaching any extra hardware. It has limit switch feedback and has onboard motion control using motion magic, which like allows like accurate timing between trajectory points. It has LED indicators that blink proportionally to output speed, and it has brake hose calibration and integrated pit control.
Can you go back? Just to know for Talon FX motors, you'll never actually see them like separately with the Falcon 500 motor itself. They will always be integrated with the Falcon 500 motor.
Thank you, Nathan. That scared me, but thank you. Okay, now we're gonna go over wire configuration samples. So you can kind of like see how like each component connects and whatnot. You see how the PDP connects like all the motor controllers that we discussed, like the Victor SPX, Talon SRX, Spark. You can see how the robot radio connects here to the robot radio, and then like here to the arm. The text is kind of small though, so you might have to like zoom in and whatnot, or like I don't know, just look more. You can see how like the robo signal light is like connected to the robo radio. Oh boy, that's go down. Okay, and you can kind of just like get a general sense of how like each component is connected to what. the pressure. Oh my god. Okay, pressure switch. Limit switch. Yeah, you can kind of see that. Here's another wiring configuration. Again, you can see the PDP connected to the breaker, motor controllers. You can see the robot that connects to the robot radio, which connects to the radio. The robot signal line connects there, and yeah. And again, this is our like last year's schematic, so you can like see how that kind of goes around, and like the can loop, like how it loops around. Right. Yeah, I think that's it. Are there any questions or anything? I'll take that as a no. Okay. Um, yeah, that was pretty short. I didn't fill up the entire hour. I kind of went through it a bit fast, but it's okay.
Can we explain more about like the layout for our FRC control systems? Can you explain more about the layouts for our FRC control systems? Like if you go back a few slides, you showed some images. Yeah, like those. We could
Oh, the what?
explain it a bit more. Yeah, we can go
Huh?
more in depth because this is like what we actually use.
Yeah, yeah. Um, is there like anything special, uh, like anything particular, or just like
Well, honestly, in general, I think. Can you explain why we? Actually, never mind. I don't really know what to explain specifically, but this is something that we should probably study. That's just what my instincts are telling me.
oh, okay. um, 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 yeah. I guess we can like look a bit close, more closely at it, but um, uh, yeah, I don't like, yeah, I don't like, I don't know what more to say, honestly.
Pipe in a little bit.
Yeah.
So I think Chung is kind of just asking more of like not exactly just going in depth to what the control system will look like, but maybe how it's like laid out. The layout for each electrical system looks different each year because we have different like mechanical systems. So the like electrical aspect of the robot is heavily dependent on where the mechanical actuators are placed. So if you're placing like an arm, for example, in the complete middle of the robot, then you obviously can't have electronics in the complete middle of the robot because that's where the arm is supposed to go. So instead, you might build like another board that's upright. So you put electronics up on that, or you could put some like electronics on the arm, but that presents its own issue. So control systems each year change just dependent on what the robot looks like and behaves. So there's no like formal way of how to build an actual control system for an FRC robot. There's like necessary parts that we need. Like we're obviously going to always need a fuse. We're always going to need a PDP and all that stuff. But the way it's laid out changes per year.
Sorry, my cat was being annoying. She's outside right now, but yeah. Any other questions, or is that it?
Actually, to just go more into detail about what Fernando was saying, let me just present my screen for a second. Yeah, so pretty much each year, the robot looks very, very different depending on the game. So what we have here is last year's our 2020 robot actually, and so we had multiple manipulators, such as an elevator slash climber right here and right here, where these like hooks kind of hook onto like raise and lower to go onto a bar. This green wheel here with a motor, that is to spin a control panel or like a large disc. And then in the front, we had, it's not in this image yet, but we had another manipulator. It was a power cell manipulator, which pretty much intaked and outtaked like these foam dodgeballs. And so as you can see, we have a lot of our electrical components in the back here. Pretty much this is the PDP. We have motor controllers all aligned right here and things like that. The Robo Rio is right here and the battery is contained right here. So what you want to do normally is have the motor controllers very close to the motors that they're controlling. So for these Neos right here, the motor controller for those is actually this like white little box right here, all the way down here. And pretty much why you want to do this is kind of just to make sure that it's easy. It's easier to wire up with the motors because they're so close together. And the only issue is that like you would have to wire the power cables so that they're actually they're longer, so they actually reach the motor controller. And then the other benefit is that it's just easily identifiable, like which motor goes with which controller as well.
Cool.
Yeah, so actually our schematic is on these slides too that we used last year. So I can
Wait,
go.
say that again. I couldn't hear that.
Oh, sorry. Our schematic that we used last year, like basically what was shown in Nathan's picture. So I'm not sure if you went over it.
Oh, I didn't. Yeah,
This
I
one.
like. Yeah.
Yeah. So basically, what Nathan was talking about was like these sparks right here. It was like right next to them. So if you were able to see those motors, but yeah, those black motors in the bottomish, the left and right, those are the Neos, and then two of them would, or four of them actually, would be part of the drivetrain, and the other two would be the elevator. And then we had like a bunch of, if you notice, like we had a bunch of motor controllers, like empty, as you can see in this picture too. So what we did was we planned ahead, like in case we had added other mechanisms. Like we were thinking of doing a shooter, so we wanted to have those available also. So that's why we had a bunch of empty, usable controllers.
Cool. Um. Okay. Hopefully that cleared up some, I guess, like confusions or just like I don't know if you wanted more clarification. Hopefully that was helpful. There doesn't seem to be anybody else who has any questions. So, I mean, unless there is, but like, um,
Yeah, this at first the electrical at first can be pretty confusing. Like you have to explain it very very well in order to like to understand it. We will be sending out some resources that you guys can look at in your email. We'll send a recap email after the software meeting for today. So, but if you guys want to get a head start, here are some just 3 links that you guys can check out to look more into at first the electrical. I think these do like a pretty good job of explaining it.
yeah. Yeah, I kind of like, I don't know, I feel like a little bad because I feel like this presentation was a bit confusing and not very like, yeah, I feel like it was a lot to handle, and um, yeah, so I like always like reach out if you like need help with understanding, or just kind of like find stuff, like take it a bit slowly if like it seems like it's way too much to handle at first. But with that being said, I think this workshop is over.
What is the difference between the Talon and the Spark?
Yeah, I'll go back.
So are you talking about the which one, the Talon SRX or Talon SR? Talon SRX. Okay, so the main differences between the Talon SRX and the Spark. So pretty much the Spark can only communicate over PWM. What that means is that it has very basic control. It's really just how fast you want it to go, and just like how much like how long you want it to run. Pretty much, you cannot hook up any sensors to it. It has to be hooked up directly to the Robo Rio. The benefits of the Talon SRX actually is that you can you switch to that slide? The benefits with the Talon SRX actually is if you see that white cap on top of it, what you can do is you can hook sensors such as the the SRX mag encoder that we saw earlier. You can hook up sensors into that port, and what it's able to do is utilize those sensors. So you can you can control like the speed of the motor and like how long it spins for as well. But you can use that information to like increase or decrease the speed if it has to like reach a certain speed, and you can also use it to like see how many times the motor rotates, and so you can set it so that the motor rotates a certain amount of time, so like the robot moves forward like a certain amount of feet, like it moves forward 10 feet or something like that. Talon SRX, it's also one of the older motor controllers, but just because it's older doesn't mean it's bad necessarily. Because it's older, there's a lot more documentation on it. I think it has like a 170-page manual just for like the software documentation. So
Yeah, and then with what Nathan said, like a lot of the different motor controllers are used for different like things. The Talon SRX in general is pretty versatile in what it can do. Like you said, just because it's older doesn't mean it's bad. Like you went over the example that you can use it to figure out how to make the robot move a certain amount of feet forward using some conversion, or also this will be discussed in the next workshop in quite a bit, but they're quite commonly used for autonomous, in which a robot is controlled like using just code without a controller input. So those are usually pretty good for that because they already have all the documentation that has been compiled over the years. And then in general, that's like the go-to standard motor, the standard controller that everyone uses, so everyone will know how to like resolve an issue, as compared to like one of the newer motors such as the Spark Max.
Cool. Any other questions?
well, if nobody else has any other questions, then we could just end this crash course right here. We will also be having a crash course later at 12 o'clock. It will be our software crash course, and Arvin, our software lead, will be going through it. Thank you, everybody, and have a nice day.